Let us discuss two sorting algorithms which people claims the most advanced sorting algorithm. Actually, they are advanced sorting algorithm because not only their performance is based, but they are advanced because they have developed later on actually. Now, these two sorting algorithm again have unique property. That property is one paradigm actually, you can say, based on the paradigm it is called the divide and conquer. Now, we will learn about what exactly the property called divide and conquer principle actually it is, and particularly this kind of sorting algorithm that we are going to discuss today, it is the merge sort and then quick sort, are very efficient sorting algorithm and suitable for sorting very large set of numbers. All of the sorting algorithm that we have discussed, for example, radix sort or heap sort or insertion sort, they are good, but they are usually meant for sorting a large not large set of number, rather very small or moderate set of number. On the other hand, these are the two sorting algorithms that we are going to discuss are good for large set of elements to be sorted there. Now, so these are merge sort and quick sort, we will discuss about. They comes under the banner advanced sorting techniques, as I have already mentioned about it. Now, they basically these two sorting algorithms based on the principle I said that divide and conquer. This concept comes here whenever you are not able to defeat your enemy, I mean group, then what you can see that you can disperse them into smaller group like, okay, then you can fight them and then you will be able to defeat if you are not able to defeat as a whole, right. So, this kind of concept is called the divide and conquer. So, their idea is that if the problem size is very large and it is not possible to solve in real time or it is taking too much time, then let us divide the problem into smaller parts. Now, here I can tell one example. If your list is very large, then it will take very large amount of time to sort it. Then what you should do is that let us divide this list into smaller list and then sort each smaller list and then solve your problem, this concept. So, this concept is called the divide and conquer concept. So, a problem needs to be divided into a smaller parts, as you can see here, this problem can be divided into smaller parts. Now, if you see that this part again, the smaller part is also very large one, not able to solve in an efficient manner, then we can again divide into the smaller, so smaller parts, and this kind of what is called the divide principle divide can go on until you are comfortable with solving the smallest problem that you have at your hand. And then finally, all the results that solving all smaller problem or smallest problem, whatever you can say, and accumulating the result, ultimately it will give the solution. So, this is the concept called the divide, and then so divide, and solving all small problem is called the conquer, and then combining the result is called the combine. So, in the divide and conquer step or paradigm, there are three steps: divide step, conquer step and combine step. So, divide means you have partitioned the largest problem to smaller one, conquer means solving small problems, each small problem, and then combining means getting the solution from each small problem and then finally putting the result. So, this principle is followed in the divide and conquer, and both merge sort and quick sort are based on these two these divide and conquer principle. Now, let us consider first merge sort. What is the divide technique, what is the conquer concept, and what is the combine, that we have to study first, and then we will be able to understand how this is basically helps to sort a number list of numbers. So, here is the idea is that let us consider this is the entire list and this is very large list, suppose, okay, and this L and R are the two bound, we can say this is the lower bound and largest one, means this is the first index and this is the last index, we can say it this way. Now, these elements, this list we can divide into two equal parts. So, this is the equal part, one part, the leftmost part, and this is the rightmost part, we can say, or left list and right list. Then what we do is that this we can sort and this we can sort, and then after sorting we can then merge the two lists. So, this basically this list which is in random order, it is a sorted fashion, this is also random order, this gives a sorted one. So, this is a sorted list. sorted list of containing the element in the left part, and this is one. Now, we cannot merge them together because here this is sorted, here this is sorted, but when we join them they may not give the sorted list. So, what we actually do is that we have to combine the result into a sorted list. So, this basically combination process in this merge sort is called the merging operation. So, here actually here is the divide operation, and here you can see sorting each sub list is basically conquer operation, and then combining the result is called the merging operation. These are the three steps are there. Now, here again if you see that this list itself is very large list, then what we should do is that we can repeat the solving this problem in the same manner, right, the way we have solved this problem. Similarly, if this is also very large one, solving this part is in the same manner the way you have done it. So, this means that initially the problem of size n, now we divide the problem into size n by 2. Next time we can again divide the problem into size n by 4 each, and so on. And in each time whenever n by 4 again we merging means it will give you the sorted list of size n by 2. Here is the sorted list of size n by 2, and finally the merging two sorted list into the final sorted list of size n. So, this concept basically is followed here, and this is the idea about the merge sort. Now, here the time that is required to merge. Okay, first let us discuss about the process. What is the merging first? How we can merge the two sorted list into a larger sorted list. Actually, I will discuss about merging, then I will be able to discuss about other. Divide is here very simple, is a trivial step, because we just simply find the middle location and then decide the left list and then right list. This is the divide. Divide is really very simple, and conquer is basically we can sort the sub list. Now, sorting this sub list you can call any other sorting technique, maybe say heap sort, but actually the idea is that why you should solve this merge using heap, right? Rather we can call the merge sort again. So, it is basically the conquer is basically repetitive step or is a recursive step, and then finally the merging is basically the conquer, combining. So, this is the concept, it is there. Now, let us first discuss about how we can merge the two sorted list into a larger sorted list. So, let us consider as an input, this is the one sorted list and this is the another sorted list. So, we can start from the starting position. So, this is the ith pointer for the list A and the jth pointer is the list J. Initially, they both point to the first elements in the list. Now, out of these two elements, what we can do is that we will compare, and in the output list originally initially it is empty, and then we will see exactly who will go to this output list. Now, it will be decided the smallest number should go to the output list. Then I here 1, it is the smallest number. So, 1 will come here. Then once it is moved, so this is empty. So, then pointer will move this one, and then it will point to the 3 and then this 2. Now, next again 2 and 3 we have to compare. Then who will go? Then 2 will go. So, 2 will be here, and then this pointer will come here. Then 4 and 3, then 3 will come here. Then this pointer will move to this one. So, this way once the element is moved to the output list, the pointer automatically from which list it comes, that pointer will move towards the right. And finally, whenever this pointer or this pointer, if say suppose this list is exhausted and this pointer is here, then all the elements at the end should be placed here. So, if this is the list of size n1 and this is the list of size n2 and then this is the list of size n, this is equals to n1 plus n2. So, this is basically the merge list we can say. So, finally, this will give the merging operation. This merging operation is basically simple. So, altogether the merging operation that will take, if the two lists are of equal size, say n and then the merged list is of size 2n, then the complexity is order of n. That means n number of comparison that is required. So, this is why this is a very simple algorithm, and here we have discussed whatever I told you, ultimately it will give you the merge list. So, this is the merge operation, and this is the most what is called the costly operation we can say in this step actually. and all other operations are very simple. And here I have given the algorithm how you can write, how you can perform the merging operation. So, once your logic is understandable, then going to this algorithm is very easy. So, merging operation, it is the merging operation is algorithm for the merge operation here, and then so that totally this concept is basically called top down divide and conquer and recursive procedure. That algorithm, these are quicksort also same thing, is a top down divide and conquer recursive. Top down means initially start with the large list, then go down, so it is called top to down, and then divide and conquer. Each time we divide and conquer, because each time we divide, solve and conquer, divide, solve and conquer, like. And finally, it is called recursive because it calls the same procedure again and again, and that is why this algorithm can be termed like this. So, this is basically the algorithm merge sort. The first is basically find the middle location, because we have to divide the list, and then again call the same procedure, I mean merge sort, but for the smaller list, that is the sub list, we can say left part of the list, and this is also right part of the list, and then we call the merge. So, here this is the divide operation, we can say, and this is basically two conquers because we are solving, and this is the combine. So, this is the divide, this is the algorithm actually, and you see we just go from top to down. This is starting from the full list, whole list, then again divide, and then whenever we call it again, this again do the same procedure as it is like this, again divide and again divide, it also divide, and this is why it is called the top down. So, initially top is basically this one, and then go down, and finally it solve the problem. So, that is why if we draw the recursive tree, that is why recursion tree it is look like this actually. What I told you, that recursion tree is look like this, as you can understand from here. This is the initial list, so sub list, divide, then again sub list, then it is basically complete because we cannot sub, because it is the termination condition, only the list contain one element, then merging, so the merging, and this one, and finally this one. So, this is the left part. Similarly, if you follow the right part, it is there. So, this whole thing is called the recursive tree actually, the way it occurs there. Now, this is for these elements, and for the other element list also you can draw the recursion tree actually, but ultimately we do not have to do the recursion tree, or it is not required, it is just mere for explanation. But whenever actually the compression takes place, the everything taken care like, and as it is a recursive procedure implementation, so each time it basically follow a stack to store the result. For example, this is the initial list, then this one, so stack will be called to push this list to store there, because it will try to solve there. Whenever it is solving there, stack will try to call this one, then here also stack will try this. So, these elements are put into the stack as you see here, and whenever the finish, that means this is the termination condition, then stack will be, so this stack will be open. So, it is last in first out order actually, and then go there. So, so this one, then again 4, and then this basically put there, and then so this basically put there, and finally this basically put there, and it basically come here. This time also whenever we solve this problem, again stack, and then putting there, so it will come here. So, this way basically the procedure works there, and this basically internal stack is required, and recursion implementation is the task of the runtime manager, who will take care about allocating which call will go to the stack, and then which sub procedure will be invoked from the stack. All these things the runtime manager will take care, only you have to write the program, and writing the program is that algorithm implementation, that algorithm actually. Writing the program means you have to implement this algorithm. Now, implementation of this algorithm means we have to define this procedure, this is the recursive one, and we have to define this one. So, merge procedure needs to be defined only, and then just write the main code here, and we will give a programming demonstration. Once we discuss everything, then you will be able to understand so how it works actually. So, anyway, so this idea is very simple actually. This is the algorithm that you have to follow, and this merge algorithm that you have to write the code. it is enough for you to solve the problem. So, it is so simple. Writing the code is really very simple if you are a little bit efficient or skill about how to write the program in a recursive manner. So, all quick sort, merge sort is basically recursive sorting algorithm. Now, so this is the sorting algorithm. The time complexity of the sorting algorithm I can tell this way: if T n, this algorithm is basically given details, right, in a very simple way I can tell about. If T n is the time complexity to sort using merging operation, merge sort is T n for the number of elements n. The first is that we have to first divide. Divide takes only very small amount of time, let it is C. Then we have to divide the two list. So, two list and solving the two list again in a recursive manner. So, it is basically 2 n by 2. So, this basically if we continue this recursive explanation, okay, if you solve the recurrence relation actually, then ultimately you can check that complexity is order of n log n. So, that detailed discussion of the calculation you can find in any standard book including the classic data structure there also. The details about this step it is discussed. Okay, so, this is the procedure about the merge sort. Now, let us discuss about the quick sort. Quick sort again based on the same principle, that is divide and conquer, but here divide technique is different, conquer is different, and then combine is different. Now, but again like merge sort, it is also top down, divide and conquer and recursive, that means recursive return is there. Now, let us discuss in this algorithm which is basically the divide step, which is the conquer step, and which is finally the combine step. In this divide and conquer procedure, the divide step is called partition. In case of merge sort, the divide is basically simply finding the mid location. So, their divide is very simple, but here divide is basically more crucial, more critical. On the other hand, in case of merge sort, the conquer is basically recursive, but the combining is there costly because merging operation, and here you will see the combining is very fast. So, these are the analogy, the comparison between the two sorting technique. Now, in case of merge sort, okay, let us first discuss about this divide and conquer, then we will come back to this comparing the two sorting technique. So, here divide concept is basically called the partition. The partition concept is like this. So, suppose this is the input list that is given to you, and you have to take any one element, let the first element, and this element is called the pivot element. Now, what we have to do is that we say pivot element, as this is a random number, it can be any value. Now, pivot element should be placed in its final position. What is the meaning of final position? The meaning of the final position is that it should be placed in this list in such a way, for example, it is placed in here, that means this element is placed, but in such a way that all elements in this part of the list is less than this value pivot, and all elements in this list is greater than this pivot element. Now, this actually see consequence is that, meaning of this is that this element placed in final location, because it is not required to move anymore, because all elements here they are basically smaller than this one, all elements here greater than this one. So, this is already placed this one. Now, here partition, this is called partition. Partition means we have to select any one number, say the first number, and this is the pivot number, place it in the list in such a way that it will divide two parts of the list. Now, this part is called the left list and this is called the right list. Now, here data not necessarily in sorted order, here also data not necessarily in sorted order. Then what we have to do is that we can again sort this, and this sorting again can be called using the quick sort for this, but here for say n, but here will be around n by 2. So, this part also n by 2. So, there is basically divide, and then conquer is basically solving the same, right, solving the smaller problem using the same procedure. This is the conquer, and finally here there is no combine, because here automatically default combining because they are already placed here. So, combine is nothing here. So, here only expensive task or operation is basically partition. Now, let us see how this partition operation can be done. There are many algorithms available in the book here and there. So, partition can be followed following any one book. I am telling you one idea about so the how the partitioning can be done. So, idea is that this is suppose L and R the two extreme location, and this is the part of the list, okay, whatever it is the list in initial list where we have to place the pivot element into its final position. Now, from here we have to look at there and we can swap this element if we see that this element is greater than this element, because always its this side should be greater than this pivot element. Then once it is there, then pivot element will come here, then the element will go there, then again from there we will check it and then we will follow this direction. But whenever we move it, we see that whether all elements in this part is less than the pivot element here or not. So, whenever we are here and looking here, we always see that the greater element, and whenever it is here and looking from here, we see that elements are less than there or not. So, this procedure will continue and we will stop here whenever we see that both these L and R moves into the same position. Now, let us explain this algorithm, this one example here. So, suppose at any moment the pivot comes here and this is there, right, and we just move into this way, so that it basically we can move this pointer if we find that this element is less than this part actually, then because this should be if you place P, then it should be less than this element, that is why the logic. So, if we see that if this pivot element, and we can move this pointer if we see that this element is less than, that means in other words we can say we can move or swap this element to this element if we see that any elements is greater than this pivot element, that concept it is there, okay, because swapping will take place or this movement will stop or halt whenever we see that the element which is basically pivot element is greater than this element, then we can halt. Otherwise, if it is less than, then we have to move this one. So, finally, it is there. Now pivot come here and this element here, then again we repeat the same procedure, but in this direction pointer will move here, the L will move in this direction. Again, whenever we see the pivot, we will check that whether this pivot element is greater than the element which is basically under scanning. So, if we say that it is greater than, then we will just okay, if this pivot element is greater than, then we just simply move it, and as soon as we see that pivot element is less than the element which is basically here, then we can just halt this movement and stop it, and then pivot will come here. So, this way pivot will just swing from here to there and again pivot is there, again we can start from here, and this the same procedure will continue. Let the pivot come here, then pivot again, right, then the next will come here, and then let pivot is there. Now, this way, so left and right actually moving towards each other. When we see that left and right basically they come in the same place, then we can say that pivot is already placed in this position and we stop it here. So, this is the procedure that we can think about, and that procedure can be explained with few more steps, and the algorithm that the logic that I have told you. So, this algorithm is implemented here. So, this algorithm you can take your own time to go through and then understand about it. And so, this is basically the procedure called the partition, and which is the most important step it is there. As an illustration, I can take some time from you and then we can discuss about it. So, this is the pivot element and this is the rightmost element, and as we see the pivot element is greater than 33. So, what we should do that we should swap it. So, pivot is coming here and 33 goes there. So, just swapping, okay, and then we have to again repeat it, but from there, because 33 is considered, we should not consider next element we have to. Then again we have to check that if it is less than, then we just simply move it, right. If 55 is right, because these sides the all elements should be less than this 55. Now, 88 is basically greater. So, there again swapping is required, because 55 that means that element should be the less than, then only we will be able to move it. As if it is greater than, we have to stop the we have to halt the movement. So again the swapping is required. So 55 will come here and then 80. So here the 88 will come there. Okay. Okay. Now this procedure maybe in the next slide we can explain it, so that we can understand about. Here is the next slide. Here you can see. So 88 comes here and 55 plays here. Now 55 here, again we can start from here. Now again we see that 77 is greater, so again swapping is required, right. So 55 will come here and 77 is come there. Yeah, we just move it whenever we see that it is greater than, we can move it. So now 55, okay, I can just clean this part better, right. Now let us start it again, right. So pivot is here, we have to start from here. Now we see that 55 is less than 77, so we can move here. Now this 66 is also less than, so we move here. So finally we come here when we see that 55 is greater than 11. So this requires shifting. So what shifting is that? 11 will come here and 55 will go there. So this movement will come there, right. Then actually here 55 will come here and 11 will come here. Now this possibly let us see in the next slide that we can think about. In the next slide we can see. In the next slide, as we see, 11 goes there and 55 come here. Now we can start right. We can start checking from here, and it will continue if we see that this element is less than this element. So it is this one, because 20t is less than, so pointer will come here, and whenever we come here 99, as you see that it is greater than, so they needs to be swapped. So this part again explain into the next slide. As we the next slide, as you see here 55 and 22, so they can be removed there, right. Now here 55 and 44, again we can check it, right. This is this one and this, and then we can say that this is basically less than, so again swapping is required. So this swapping is come here, and then left and right you see with this swapping they can come to the same place. Now at this position, whenever this left and right come to the same place, we see that this element always, that this list contains all elements which is greater than this element, and this list contain all element which is less than this pivot element. This means that this pivot element 55 is placed in its original, this is its final position, and these are the right sub list and this is the left sub list we can write, and then we can call the same quick sort method on this sub list again, the same procedure, but it is the number of list is reduced to half actually. So this is the procedure that we can follow, and so this is basically the partition. Partition is the main task here, and that is the divide procedure we can say, and then the conquer is basically sorting the sub list, and combining is implicit, we do not have to do anything here. And this is the algorithm that we have given, the total quicksort algorithm. First we have to partition, given the left and right, this is basically the two boundaries of the list. Then again we have to call the quicksort, this is the termination condition, recursively we can call, this is for the left part, left list, and this is the right list, and that is the quicksort algorithm. So now, so this is recursive, so this is the quicksort itself, we call the same procedure again and again, and here is the partition algorithm. That algorithm I have already discussed about, that is the only heavy algorithm, otherwise everything is very simple. And while we discuss the programming, that time we will be able to understand that how nicely it can be programmed, only to write the code for write partition and then just quicksort in a recursive manner. So this is one example that we have used for your illustration. This is the total list. So pivot is 55 and then go on recursively. So this is the recursive tree actually, how it go, as is 55 partition the list. So this is the input list, 55 is the pivot, it plays then again sort it, 33 is the pivot, 33 placed left and right. Now 22 is a pivot, this is empty, so stop, this is only one, stop. So this basically already sorted. So 11, 22, 33, 44 and this way 55, you see all these elements are already placed in their order, this part, and this part also if you see starting from here. So 99 is placed, then 88 placed, then 77 is placed, then 66. So this is also placed, so this order. So whenever you do it, they are basically automatically the final position gives place them. So we do not have to do any other procedure for the combine, it goes this way. So this is the procedure that you can think about our quick sort algorithm, and so far the time complexity is concerned, it is very similar to the merge sort. So only the partition, the time that is required for this, actually the time complexity that it is required, if you say the for the n number of elements partition. So it is a for the partition it require around n time, it is basically n minus 1, we can say n minus 1 comparison is required for the partitioning, I mean to place the pivot into its final position, plus next is basically 2 parts. So it is basically this is the partition algorithm, and this basically 2, if we say the 2 list of equally size, say half, then this is the complexity of the algorithm, we can say. So it is basically written in this way, it is like this one, right, and the details discussion of this complexity analysis here we can say it is around this one. So it basically this complexity analysis, it can come to you same as order of n log 2n. Now detailed discussion and then the procedure about this complexity analysis you can find in any book including classic data structure that you can consider. So this is the complexity. Now this algorithm is basically more or less, I mean same complexity than the merge sort, but there are certain comparison that we have to think about it. Now this comparison is basically important when there are best case, worst case, average case also. Let us first discuss about the best case, worst case and average case, and this is the worst case. The worst case occurs when we have to sort a list which is already sorted order, already in sorted order. So in that case the time complexity that can be expressed in this formula, this is because this is basically to place the pivot element n minus 1 comparison, then it leave only one list, the size of the list is basically again n minus 1. Now this part if you go, then it is basically n minus 1, this is there, and if we it is, then it is basically n minus 2 plus this basically t n minus 2. Now if we factorize it, so all these things will come, so n minus 3 plus t n minus 4. Now this way if you continue, so finally this will gives you n minus 1 plus n minus 2 plus continue 3 plus 2 plus 1, because this is the final termination condition. Now this basically the total time that is required, you can check it, n into n minus 1 divided by 2. So this basically complexity is in the order of n square. Now so in case of worst case time that is required for the quick sort, it takes order of n square time. This is comparable to merge sort actually. In case of merge sort it took order of n log n. So that is why the quick sort is termed as, it is nothing but quick when the list is already in sorted order. So definitely quick sort works worst when the input list is in sorted manner, but it is actually, so that depends on, right. So in most of the cases usually we have to sort the list which is basically not in order or any order. So that case is rare rather. So this way it will not be a big issue for that, but quick sort is really, that is why it is called the quick compared to the other sorting algorithm. And in this book you can find the comparison of different sorting algorithms and the graph we have drawn. Then you can check that if the number of elements increases, then how their performance also changes. So, that trend you can understand, then you can decide that which algorithm works better for you. Now, so we have discussed many sorting techniques, merge sort, quick sort, these are the advanced, and then there are some good sorting algorithm, heap sort and then radix sort, and finally we have discussed many simple sorting algorithm like bubble sort, insertion sort and selection sort. Only few sorting algorithms have been discussed in this course, but there are many more sorting algorithms are there, which are also, they have their own good point, pros as well as some limitations in each them. So, those things you can learn if you want to learn much more about many sorting techniques. That books, classic data structure, you can consult, you can find many ideas from there. Details algorithm, illustration, the comparison, analysis, everything in details you can find from this book. Okay. So, with these things I would like to stop it here today. Next portion that we will discuss about programming aspects. So, what are the different sorting techniques that we have discussed, how to write program. I will give a hint about how to write the program, but my advice is that you should learn the logic, algorithm if required you can follow, and then write the code of your own. That basically matters to improve your programming skill. So, this is the one good point, that sorting and searching algorithm usually most programmer take up their cases to hone their programming skill. So, you will get that opportunity to improve your programming capability if you want to implement all those sorting algorithms of your own. So, thank you very much.